In today's lecture, we'll be looking into one of the problems where we have experimental kinetic data, and from that, we'll try to find the order of a particular reaction. Before we jump into solving the problem, let's have a look at all the equations we have derived in last few classes. So, okay, this is not very good. Let me try it again. Okay, I think this is the best we can get. So we have derived the equations for the zero order. We have done the same for the first order, where the reaction was A2 products. For the second order, we have done two cases of elementary reactions. So one where the initial concentrations of A and B, the reactants were not the same. And in the other case, we started with the same concentration of A and B. We have also looked into one of the non-elementary second order reactions, and in the last class we have derived the nth order, and from there we have looked into the fractional life method. So in today's lecture, while solving the problem, we'll be using some of these equations. Okay, now let's have a look at the problem statement, the one we'll be dealing with today. What is that? I think this is the one. So you can see the reaction is A2 products, and the order is not mentioned. We do not know whether the reaction is elementary or non-elementary. We have the overall reaction for the system. So A is the reactant, and we can have one or two products or multiple products out of this reaction. And the composition of A in the reactor is measured at various times, with results shown in the following columns 1 and 2. And we have to find the rate equation to represent this data. So in column 1, we have time data, and in column 2, we have concentration data. For the time, we have started with time 0 up to 300 seconds, and the corresponding concentrations are listed in column 2. So our approach would be, so far we have seen integral methods of batch reactor data analysis. So we'll be using that for this particular reaction. And if we can recall the expression, so for the first order, the expression is something like this. And for the second order, so there is only one reactant. So if we want to check whether our experimental data fits with first order or not, we have to make a plot of CA versus non-CA versus T. And if we want to check our data for second order, we have to plot 1 by CA versus T. So using our column 2, we have to calculate both ln CA and 1 over CA to check whether the data is fitting first or second order kinetics. So finding ln Ca or 1 over Ca is not very complicated. So if we look in here, again, I'm writing down the expression. For first order, we have ln Ca by Ca naught equals Kd, which can be rewritten as. So if we plot this one, um, and so instead of just ln Ca, we can plot this in y-axis and t in the x-axis, and the line should go through origin. If it is straight line, then we can say it's a first order kinetics. So we'll be using this column and this column. And when we plot that, so we have time in our x-axis and ln Ca naught by Ca in the y-axis. And we see that the line is actually not a straight line. So it's a curved line, and hence we can conclude this data do not fit the first order kinetics. So our assumption of the reaction being a first order reaction can be rejected. Now we move into our second trial. Going back to this table again, and in column 4 we have 1 over Ca. So for order 2, the expression is let me rewrite it again. So this is basically 1 over C naught. We can plot the whole thing versus T, or we can plot 1 over Ca versus T. Both is okay. If we plot the entire thing on the left hand side, then it should be a straight line passing through the origin. If we plot only 1 over Ca, then the slope, the intercept should be equal to 1 over Ca naught. Let's have a look at the plot. So this is our 1 over Ca naught, and for this we can see that it's not a straight line again. So um, we can say that our assumption of the reaction being a second order is also not valid, not supported by the experimental data. So what do we do then? Now let's look into this experimental data again. I mean the statement. So we have seen the fractional life method in the last class. Maybe we can use that one. How do we do that? We have only one initial concentration, and for that we need a few concentrations, starting concentrations. And so what we can do here is basically plot this data. So CA versus T, we can make that plot, and from there we can figure out time required for so time required for a particular fraction at different concentration levels. Okay, so let's look into that. So here we have, on the left hand side, we have this plot of CA versus T, and here we had this data of CA naught 10, and then the concentrations, the later concentrations were 8, 6, 5, 3, 2, and 1. So we can go for different approaches. We can use any value of f. So it may be 0.5, it may be 0.8, it may be 0.4, whatever is supported by our available data, we can use that. In this worked out problem, if you look into the table on the right hand side, the F, or the percentage remaining of the reactant used, was 0.8. Okay, so in that case, so we started with initial concentration of 10 mole per liter, and if F is 0.8, then our Ca with 80% A remaining for 10 mole per liter would be 8 mole per liter. So we have the data point in our table, and so it's easy to figure out the time required to. So TF1 at Ca naught equals to 10 mole per liter. We can get it from the table straight away. It's 20. But if we look into the numbers here, instead of doing that, what they have did during solving the problem, they actually use the curve instead of this discrete data points. So if you look in here, so we have Ca naught 10 and Ca 8. Using the plot and the distance between the time for Ca naught equals to 10 and time for Ca equals to 8, the required time was measured. So it's, instead of 20, it's 18.5. The second data point here is 5 and 4. So again, the initial concentration here is 5. So it's the second Ca naught. And with F of 0.8, the Ca is 4. And the time required to reach a concentration of 5 mole per liter was 59 seconds. And time to reach the concentration of 4 mole per liter was 82 seconds. So the time required for conversion from 5 to 4 is difference between these two, and that's 23. And a third data point was selected with a CA0 of 2 and with a fraction with a value of 0.8 for F. The CA3 would be 1.6, and for the time required to reach from 2 mole per liter to 1.6 liter is in fact 35. Now, it's a matter of understanding the process. Like, this is a question to you. Like, why didn't they use the tabular data, and why did they go for the extracting the data from the curve? So uh, it's a question from my side to you, and I hope you'll be able to think it through and realize why they did it instead of using the table. If you cannot figure this out, we'll discuss this in one of the next lectures. So now from the curve, we have 3 values of CA0 and 3 values of TF. So we have these values. So now let's look into this fractional life method equation. If we remember from our previous class, and I have also shown the expression at the beginning of today's lecture. So our TF is basically F to the power 1 minus n minus 1 over Kn minus 1 CA0 1 minus n. And when you take a logarithm of that, the expression becomes log TF. It can be ln or natural log. Either is okay. Here F is 0.8. K we do not know. N we do not know. Plus 1 minus n log of Ca. So now we have 3 data points for Ca. Pardon me, this should be Ca0. So we have 3 data points of Ca0 and Tf. So we can easily plot that, and from the slope we can find out the order of the reaction. So let's have a look at the plot. Here it is. Okay. So we have ln Ca0 in the x-axis and log of Tf in the y-axis, and we have a straight line with a slope of negative 0.4, which gives us an order of 1.4 for this reaction. So probably now we can realize why the data could not be fit for the first or second order. And if we look into the plots again, let's have a look at the plots for first and second order. So this was for the second order. And if we look into the first order, so we can see there is a change in the shape of the plots. So from first order to second order, the shape actually changed. So in one case, the shape is concave, and in the other case, the shape is convex. So which is probably an indication that the order probably falls between these two. And from the fractional life method, let me bring it again. We can see the slope is negative 0.4, which gives us an order of 1.4. So probably those plots already gave us an indication that there is a chance of the order being in between 1 and 2. And with a fractional order, no way you can um, use integral method, because it's an iterative process, and probably you have never imagined of it being a fraction and haven't derived the equation for the fraction. There are so many options, so it's practically impossible. Now, again, uh, so we have this equation where TF is 0.8 to the power 1 minus n, which is 1.4 minus 1. K, n is 1.4, and this is 1 minus 1.4. So let's take one of the CA0 and TF values. So for CA0 equals 10 mole per liter, our TF was 18.5. If we put these numbers in this equation, then we have only one unknown in the entire equation, which will give us the value of K. So what is the unit of this K? Very important. So we figured out the order of the reaction, and also we figured out the value of the K. So let's write down the rate expression. Our rate expression is something like this. And here n equals 1.4. What is the unit for this equation? So usually, since we are using RA, which is basically the reaction rate in terms of volume of the reacting fluid, so the unit should be mole per liter per second. And here we have Ca to the power n, so which is Ca to the power 1.4, which makes the unit of this term um, mole to the power 1.4 by liter to the power 1.4. So now we know the unit of the entire equation. We know the unit of the concentration dependent term. Now we can easily figure out what would be the unit of this temperature dependent term or the specific reaction rate. So we can again rewrite this expression as, this is our K, this makes so this unit of K makes the unit of the entire equation as this mole per liter per second. So when you solve this kind of problems, you have to not only find the values, but also you have to find the correct unit for K. And you probably know that the unit for K varies with the order of the reaction. It's different from what it is for first order reaction to what it is for the second order reaction. And in this case, we can see it's different when we have a fractional order. So it's very important you not only find the actual value of k, you also figure out what should be the um, unit of it, and um, it also depends on how you write the expression. So whether it's in terms of volume of the reacting fluid or in terms of the surface area of the solid. So depending on that, your k unit of your k will change. So you have to be very, very careful about that. So with that, we'll be concluding this short lecture, and in the next class, we'll look into another example where we'll be using a different physical property uh, to analyze kinetic data. So here we had easy task. Let me bring it again. Here, directly the concentrations of a reacting fluid were given. So it was very easy for us to fit it um, in the equation we already have. But what if we don't have the concentration? We have uh, some other properties which is somehow related to concentration. It may be pressure, it may be, say, electrical conductivity or any other property. So how do we deal with those kind of data? Uh, we'll look into that in the next class. So with that, I'll conclude today's lecture and I'll see you in the next class.